Yes, then welcome everybody again to the next installment of our series. And today we have Dr. Elmar Neumann, who is from the University of Siegen originally and is currently at the Helmholtz Nano facility in Jülich. His expertise is in SEM, FIB, and EDX. And today he's going to enlighten us about how we can actually see the nano-bio interface that we've been talking about so far. Dr. Neumann, the floor is yours.
Okay, thank you very much for the introduction. And also, good afternoon to everyone here. So I'm going to start about how to image the ultrastructure between cells and nanofabricated surfaces that, with the help, say, mainly of SEM and electrons, basically, and the location where I'm now is the Helmholtz Nano facility. This is a clean room where most of the ultrastructures are fabricated before cells grow on them. And we also need to do this in order to investigate the success of these. So this is a rough overview of what I'm planning to say. After a short introduction, I would like to point out why we should go from light to electrons or other probes in order to image surfaces and structures. Light microscopy in comparison to TEM, SEM, and for example, AFM. And then I will spend most of the time talking about the different types of sample preparation possible or necessary for these purposes, going from resin embedding, CPD, cryo TEM, and something like this, and then to the imaging. So, okay, yeah, this is what it is all about. We would like to end up somewhere here with our investigations, with our efforts. The left one is a cryo sample, and the right one is a resin embedded sample. This one underneath here, the left one also cryo. So, and I would like to point out how to get there. Yeah, first things first. We are talking here mainly about images, and an image is a finite area, X and Y, or maybe even a third dimension, and another pixel, and another is the property. And the property from our experience, everyday experience, is coming from visible light mainly, but other techniques also produce images that somehow look like our everyday experience, but plot different types of properties or show different types of properties that in many cases cannot just be directly compared with for what we know from our own experience. So the reason why we go from light to electrons is obvious. We all know probably the diffraction limit. That means basically that the minimum resolvable distance of two objects is directly linked to the wavelength that we're using. So visible light ranges roughly from 400 to 700 nanometers. And the other parts here, N is refractive index, alpha half opening of the angle if the image is in focus. And at the beginning, before these techniques were invented, it was quite appealing to use electrons instead of light particle or light waves in order to image, because if one looks at the mere numbers, it's very appealing that we should go even below the chemical bond in this case, for example. But due to imperfection of the electron lenses that we're using here, or what we are capable of manufacturing, we end up for TEM in the range somewhere of 0.05 nanometers, or in a good SEM around 0.5 or half a nanometer in this case. Yeah, so starting from light microscopy, we all know this. the light, the source for the radiation is a lamp in many cases. Then we have the condenser that takes care that the site of interest sample here is illuminated evenly over the whole area. And then if you follow these paths of this line, you have this intermediate image, and then through the eyepiece or the projector, the objective lens, this is wrong here, objective lens, you will see the final image here and capture this either with your eye or with a camera. Going from electrons, going from light to electrons, you have basically the same setup, but this time you have an electron source here. The lenses are not made of glass or other transparent materials, but they are coils, electromagnetic lenses in this case. What they have both in this case in common is the object in this place here right after the condenser before it goes to the objective lens. Then again you have this intermediate image, and then your objective lens that will focus your image or project your image either on a fluorescent screen or on a camera. We will talk a lot about what properties these individual samples should have in this case. We all know light microscopy, of course. In many cases, the images should, the objects should be transparent in these cases, but there are also top-down microscopes, so that this is not really necessary in this case. But for the electron, unfortunately, the sample needs to be transparent for electrons. That means very, very thin, because we're talking here about a charged particle with a spin, and light has none of this, and electron has both of this. So, and that also means that in this case, we have to evacuate. We have to pump down the whole chamber here. This also has a great impact, of course, on the properties of the object that we want to observe, because as we all know, it's very easy or very common to make in vivo experiments or observations of living cells, for example, in a light microscope very easily. Everybody did this, even as a child. If you take some infusoria from the pond or something and look at this, it's not a problem. But this is not so easy or even impossible using transmission electron microscopy, because the high energy density here, the vacuum in here, and other things. So why going from TEM to SEM on losing again a bit of resolution, losing again a bit of resolution, is the fact that it's very difficult to image surfaces with transmission electron microscopy. It is in principle possible, but you have to make great preparatory efforts in order to do this. So, and the general setup, I mean, both are called electron microscope, or sometimes some put together in the term electron microscopy, but they working with completely different principles. That means, again, you have an electron source, then condenser lenses. These condenser lenses are named so because they condense the electron beam to a small spot. Then with the help of this, with the scanning coils and the objective lens, the electron beam is projected on the surface and then scanned point-wise over the surface. And then the detector is another point, is another place. We will come to this later. And again, we have far lower pressures here for some types of electron sources. And in this sample chamber, slightly higher pressures are possible. And I'm very well aware that there are, of course, environmental SEMs available so that you also can use or investigate wet samples, or with some other atmosphere, for example, water, in order to prevent them from drying out or something. But you pay dearly in resolution if you use one of these techniques. Okay, and another point here is, of course, if you skip electromagnetic radiation in the first place and do not use a light source or electron source or whatever, and you use instead some scanning probe microscope. Here in this case, I would like to show the working principle of an AFM, Atomic Force Microscope, a very thin, very fine tip. In this case, you can see here a etched tip of a silicon single crystal here is moved very closely over your sample. And in the ideal case, you your tip approaches the atoms of your surface, and at some point you, depending on the distance from the tip, from your tip and your sample, you will first experience no interactions. If you come closer and closer, you will soon see or measure some attractive forces before you again measure repelling forces. And these forces can be measured, for example, focusing a laser and on the cantilever here, on the top side of the cantilever, and then measure this very small deviations or this very small movements during this scan with a photosensitive detector. With the help of a feedback mechanism, with with this feedback mechanism, the distance between the tip and your sample, the machine tries to keep this a constant, and the deviation from this, or the effort of this, will be recorded as a function of your position here on the surface, so that you can get either a line scan, or you can get information here about the height. And you can, with this mode, you can get even sub-nanometer resolution in this case. Okay. I would like to point to this point here. There are far field and near field devices. Far field are, for example, all those machines or devices where the detector is very far away from the source and from the object, so that they do not play any greater role. But the near field, to which these AFM belongs, is where the roles of the source, the object, and the detector are not clearly distinct anymore, because so very, very close to your sample. Maybe, yeah. Okay, here are again here's again a comparison between the different methods, from 1 meter to nanometer range, and here you can see the different and overlapping areas of parts where you can use the different methods here in this case. Here we have some machines, light microscope. Everybody knows this is a quite old transmission electron microscope. This does not exist anymore. It has been demolished a couple of years ago already. It's quite large. Here under this lid here is the screen where you can observe it, all your image here, also with a small microscope here, light microscope here. Your sample goes in here. That makes the sample size very small. It's about 3 millimeters in diameter, but we will come to this a little later. This is an old SEM. You have a large, again, a column, what we were talking about. We have a large opening here for all kinds of samples and sample sizes, as well as a cryo transfer system. And this is a modern day AFM machine. Yeah. Okay. What? Did I miss something? Okay, this is how an SEM works. Again, we have the source somewhere here. The lenses are electromagnetic lenses, which are coils and operated by alternating current. Then we have the different condenser lenses, and here the objective lens. This is the path of the electrons through this one here, and the electron beam travels through the column, will be condensed and then focused on the surface of of the sample, and then scanned over the sample line-wise. And in these lines, with the help of the scanning coils, it stops at distinct points to record the outgoing particles. We are going to talk about this a little later. These electrons or these particles will be detected, amplified, and then with another set of scanning coils, for example, represented on a TV screen, so that again, an electron beam will then be moving over the sample, over the screen, and this motion is synchronized. The one over the sample and the one on your screen. The magnification in an SEM is simply because you keep the aspect ratio and the numbers of lines and points in these lines constant, but you reduce the area that you scan, and over time, and the electrons that you detect come from. No, this is something else. From these distinct points here, and the resolution and the Ortsauflösung. The resolution, the sensitivity for the different points here simply comes from the position of the electron beam here itself. And while we are also working with SEM here in most cases, it's also possible to use, say, other charged particles apart from electrons. For example, using in a focused ion beam, an ion beam made of individual metal atoms, of metal atoms. So instead of having here an electron source, you have a liquid metal ion source. We mostly use here gallium, but in many other cases, you can also buy machines with low melting alloys, so that you can even, these are also heated in these metal wet, and again a tip, and then are ionized and then ripped off this tip. These ions are ripped off this tip, also travel through the column, and again, in this case, we have electrostatic lenses, also travel through the column. Also a fine ion beam, in this case, metal ion beam, will be formed and then also scanned over the surface in order to, in this case, to manipulate the sample. Another special case is also the use of say, other gases, not metal, they are quite heavy. You use one can also use lighter atoms, just like helium, for example. In this case, you have a helium source in here, helium gas, and a very cold tip here. I mean, we want to condense helium at this tip. And then again, by field emission, these atoms are ionized. They travel then, again, they travel along with the help of magnetic fields through the column, and then also projected on the surface. And as you can imagine, going from a quite heavy metal atom to a lighter atom is obvious, because you would like to, say, minimize the damage, for example, or if you want to, for example, use this for patterning, and you, for example, for 2D materials, helium ion microscopes are used for doing so with 2D materials such as graphene, for example. Yeah, coming to the sources, there are basically two fields or two main sources for electrons. This one here, LAB6, represents a thermionic a source. So the electrons, this single crystal, LAB6 single crystal, will be heated to a couple of thousand, no, 1,600 degree or something. And then electrons will be emitted here from the top, and then again will be extracted from here with the anode, and then travel through the column in order to be projected on the surface. On the other hand, you would like to have, say, the quality of an SEM image depends on the brightness, and you want to have as many electrons as possible on the surface, or on your sample and in your beam. So another thing is the field emitting sources, where you again have a tungsten, needle, but this needle here is covered. I can see here some other parts in here. This was once a zirconium oxide reservoir, and then this zirconium oxide on top lowers the work function for the electrons for this material significantly, so that you do not need to heat up so high in temperature as, for example, a thermionic source, and you get far more electrons. You get a better brightness on your surface, on your sample in this case. Yeah, this is a typical LMIS, a liquid metal ion source. Here in this very small cylinder here, these are heating coils. Gallium 69 is put in here because of special reasons. We would like to have, isotopically clean gallium in this case. And again, the melting point is around 40 degrees, and then this and this liquid metal then again wets the surface of this tungsten tip again, and then at the tip again with very strong fields, electric fields, the atoms are ionized and then also accelerated back from, where's my mouse? Accelerated back here, and then also these ions travel through the column onto the surface. Okay, the other part here I would like to go through quickly is, let me go back, is this part down here. It is here the objective lens. This one is responsible for focusing the sample, the electron beam on the sample, but also, unfortunately, if the electron beam hits the surface, this is the surface of our sample, in this case a tilted one, the electrons we are interested in here are the Se1 electrons. They come from here, from our point of interest. But unfortunately, we also create a bunch of other signals that do not directly come from here because of, we will go into details about this a little later, they may be generated somewhere else on the surface or from the chamber wall, and will also overlap with your original signal and therefore blur your signal or deteriorate your information. So that's why people invented these inlens or these snorkel lenses. That means in this case, the electron beam is not conventionally collected by a detector, but with a magnetic field accelerated back into the column and then projected on the so-called in-lens detector. The in-lens detector is named so not because it's inside of the lens, but once the sample even is inside or put inside of this magnetic field, the sample becomes part of the lens system. It's not outside, it's part of the lens system. And that's why it's in the lens in this case. So, and this is then more likely that only our SE1 electrons will be detected and not all the others that may come from chamber wall or somewhere else from the surface or the sample. Detectors. So we need to detect these electrons somehow. This is one of the original detectors here. Here's a very old one here, disassembled. You have a scintillator here at the top of a light conducting rod here. With the help of a bias, the electrons are the electrons that you created in your sample are attracted by this bias and then interact with this scintillator. Then a light quanta, a flash of light will be created. This light will be then directed to a photomultiplier and then to an amplifier. Then the will be enhanced, the signal will be enhanced by this photomultiplier and then transferred back into an electrical signal in an amplifier and then goes onto your screen. Yeah, maybe I put this a little later. So, of course, there are combined machines possible and available nowadays commercially, so that we have both combined in one machine. A SEM-FIP in this case, we have an electron beam and electron column and an ion beam column combined in this machines, so that we can make use of both of these effects here. We see here very clearly the differences using gallium versus that of electrons. It is simply the mass. The mass of these ions, for in this case, gallium ions, is far larger, and we use this for manipulating the surface for adding, so to speak, the third dimension to this two-dimensional SEM image. So this is what we can do with what is done normally to a surface using gallium ions in this case. And what is also very important, what I will also talk about a little later, is this gas injection system. This is also vital for producing these kind of images. So in this case, we have a crucible where a metal organic precursor, platinum metal organic precursor, is put, and this is vaporized under the conditions in the SEM or in the focused ion beam machine, so that through this needle, these gas atoms will adsorb to the surface and will either be treated by the electron beam or the ion beam in order to start some electron or beam-induced chemical vapor deposition on the surface. Here on this image, you see two small patches from either electron beam deposited material from this, what we call platinum, but really indeed this is of course platinum, but also say it is platinum nanoparticles inside of a carbon matrix. If you use ion beam induced deposition, then of course you get in addition far more gallium in this case. You get gallium in this case also incorporated into this into your patch here. So this is what an SEM or the focused ion beam machine looks from the inside if you were the sample. So this is what you would see. This is the electron beam column, the electron beam column, and the electron beams come from here. Ion beam, between electron beam and ion beam, there is usually an angle of 52 degrees. There are a couple of detectors. And here again, you see this mesh from this secondary electron beam detector. And behind it, you see this white glowing, this is a scintillator. And the electrons that go back in this inlens mode, back into the column, are transported here, are then moved through this light conductor in this one to the same amplifier in the end. Okay, if your electron beam hits the surface of your sample, here are a few Monte Carlo simulations of always silicon and with different acceleration voltages. This is always the surface here. The electron beam impinges here at this point each time, and we go here from 20 to 10 to 5 kilovolts. And once the electron beam hits the surface, it will start an electron interaction cascade. So that will distribute into your sample over a couple of nanometers or even microns in this case, depending on the acceleration voltage and of course on the atomic number of your material. And what I would like to point out is that even though your incident electron beam is very small, say in the range of 1 nanometer, still the whole volume answers to your signal. So that means you do not only get your signal from exactly here, but from in principle from all of this volume. The red trajectories are those electrons that leave the surface and can be detected by a detector in the end, so-called backscattered electrons in this case. So electron beam hits the surface. Again, you have this interaction volume, and then you create quite a bunch of different particles. For example, and also these information come from different depths inside of your from your sample. The largest one is cathodoluminescence. I will not go into details about this one here. Then the next range, again, it depends both on the energy and of course on the material, the real sizes here. Then next one is X-ray Bremsstrahlung, gives rise to the continuous spectrum, but we're going to talk about a little later. Next one is the, is that correct? Yeah, the characteristic X-ray spectra or lines, then backscattered electrons, and the smallest portion, the smallest volume increment comes from secondary electrons. And we are mainly interested in these secondary electrons for observing surfaces in this case. Yeah, and then also, if your sample has a finite thickness compared to the electron beam and to the penetration depth, then you also can detect transmitted electrons going through the sample. Right. Okay, so first, secondary electrons. Secondary electrons come from inelastic interactions with the atoms of your sample. So the energy, they lose quite a large amount of their energy. They do not have, say, 5 kilovolts as the incident beam, but only some 50 electron volts that is left. And this detector and this signal will be used for creating the so-called topographic contrast that gives us information about the surface itself and the structure of the surface. Very important in this case is also the effect of of edge enhancing. You see here the line, this edge here, for example, is glowing quite bright, even though it's supposed to be the same material over here everywhere. This has something to do that the probability of secondary electrons, that the probability for the exit of secondary electrons is far higher in these regions at these edges rather than compared to the flat material. This is also a very important effect of this topographic contrast. So in a sense that, for example, a rougher surface of the same material may look far brighter, and then may lead the observer to think that there may be another material present, for example, even though it isn't. Okay, the second is backscattered electrons. Then these electrons are, they interact more or less with the nucleus, and then they come from elastic interactions, and they scatter at the nuclei of your material, and therefore give rise to the Z contrast. It is the atomic number contrast, and here's the same image recorded with backscattered electrons and giving a better distinction, or you see the difference between these different materials far better. This is a drop of solder I found the other day on the floor here somewhere in our building. And you also see that this edge effect is far less pronounced, if visible at all. Okay, then next, what could also happen is if your incident beam kicks out for example, K shell electron, and this electron, this vacancy, is then recombined by an electron from one of the upper shells, from the higher energetic shells of an atom, and this will emit characteristic X-ray. In this case, this can also be used in order first, of course, to detect and to determine the elemental composition of a sample, but can also be used for mapping. And as we saw before, the interaction volume for this type of particles is far larger. That's why we lose again a bit in resolution. Here again, some mapping only, in this case, only looking at the tin L series, and here the lead, and you see these are complementary images in this case. Well, another from a technical sample here, different materials with different colors in this case in order to get this overlaid image. Here again, a comparison between all of these. You see first more topographic, then next more Z contrast, and here we can clearly say what elements we are talking about. Yeah, the last one here in our case is the one with transmitted electrons. A bit like in transmission electron microscopy, it's also possible to measure those electrons, the primary beam that goes directly and is then distracted from its path by the sample here itself. It's a retractable detector. Again, the sample needs to be very thin, or the particles need to be very small in order to observe these. You get a far better, in this case, you get a far better resolution. This is the case where you can get 0.5 nanometer resolution in an SEM as well. And here you can see it's a commercially available sample of gold nanoparticles on a filmed TEM grid. We will see this a little later. Here is another STEM image taken from carbon nanotubes. This here in the center is a normal regular secondary electron image, top down, and this here clearly sees that that they are hollow, that you can see the walls here of this carbon nanotube in the STEM mode. Yeah, for the STEM mode and also for TEM, for transmission electron microscopy, these TEM grids are quite common to use. They have 3 millimeters in diameter, and yeah, there you need to prepare your sample on. In many cases, they are filmed so that you can deposit particles on top or grow cells directly, but this we will see a little later again. So the ideal sample for observation in an SEM should be a solid sample, should be electrically conductive, clean, dry, vacuum stable. That means non-volatile components, should not contain any volatile components, stable in electron beam, so should not be destroyed by the energy that you put into the system. And for TEM, the thickness should be around 150 nanometers, or smaller than 150 nanometers. Also, again, depending on the material that you're using. But for biological samples, we also have this. None of this applies to what we would like to have in a TEM. We, in most cases, have wet samples, single cell cultures, in many cases on surfaces and on structures, sometimes genetically manipulated in order to, with some fluorescent They are in liquid, most cases aqueous solutions. They are on slides, that means on glass. Nobody likes glass. And or on cover slips, same there. And these MEAs that we also so quite frequently get, they have a multi-layered systems, also again with a passivation layer on top in many cases, in all of the cases, and some ring. This is always also in the way in many cases. Yeah, and then in light microscopy, you can here guess some structure, some pillars maybe, and then of course a quite dense, more or less dense, a culture of cells in there. So how do we get these into an SEM or an TEM? Yeah, basically like this. So first the liquid, then again not by applying heat. So the proteins denaturate due to this process, and this is what we're going to do chemically in the first place. But there are, of course, protocols available where you can also work with heat and temperature in order to fixate cells and things like this. What we are talking about here is chemical fixation for resin embedding and for critical point drying, and without any without chemicals, we can work under cryogenic conditions. Okay, so first things we have our substrate with the cells on top with on a structured substrate in these pinkish liquids there, and in the first step these cells are killed and or fixated. The proteins are fixated with some kind of aldehyde. In this case, glutaraldehyde, but also formaldehyde is also quite common, or mixtures of both. These aldehydes cross-link the amino acid of the proteins, particularly lysine in this case, in order to stiffen, to make the structure somewhat harder. Next step in this case, so I skip all the washing and the rinsing and the buffering, things like this, and most of these protocols that we're using here and what I'm showing here is taken over a long time ago from TEM preparation. So what I'm talking about here is also valid for some cases for TEM preparation. So then fixating the lipids in this case with osmium tetroxide and ferricyanate. This osmium tetroxide attacks the double bonds in these lipids here of long-chain fatty acids, for example, and cross-links them, going from the oxidation state 8 to oxidation state 4. That's why the color changes from no color to grayish. So, but if we look at this fixated sample, still you do not see so much in there. And this is the problem. This is also another thing that we need to do is because our polymer is a carbon-based material. The polymers inside of a cell, of a living cell, do also not differ chemically so much. I mean, from the viewpoint of an electron beam, not so much from the surrounding materials or the embedding materials. So that's why you hardly see anything here. You do not have any great changes in density or electronic conductivity or something. So this is why we need to increase the conductivity. And for example, by increasing the density, or we put in metal ions in order to increase the cross-section for these electrons to interact with. Next thing is we stain the sample then with thiocarbohydrazide, and literature says it's for staining carbohydrates. I also need to admit that we do not do any, say, research on these things, on these protocols. So I cannot tell you anything about the differences, so with or without. The first one was a lucky case here, so that we tried staining and fixating only with osmium tetroxide. But for the others, I cannot show you any comparison except that you see something. So, but not in all cases. So this is what literature says and the protocols we apply here. Next thing is, again, this time staining only with osmium tetroxide. Again, it stains the lipids. And here you see the difference in color in this case, in these cases. After that, the heavy metal staining, or osmium is also quite heavy metal, but the next step is using uranyl acetate. And this goes to both lipids and proteins and some other. This is also true for the osmium. Even though it sometimes said it goes only to lipids and only to this or that, osmium tetroxide may be able to attack all kinds of double bonds. For example, also carbonyl, the double bonds and things like this. So they're not very sensitive. You cannot use this kind of staining for identifying individual parts of a cell or something. So, and it stains proteins and lipids. Then this liquid becomes some yellowish color. After that, we add some tannic acid. This tannic acid is supposed to act as a mordant for the uranyl ion in order to improve the fixation of these ions to different structures in the cell. After that, after the staining is done, we dehydrate the cells or dehydrate the samples by using the ascending ethanol series. After this, we use a resin mixture, again, diluted in ethanol, and also, again, in an ascending series from only a few percent up to 100% of this resin. Then, after this, we reach 100% of the highest concentration of this resin. We remove some excess of this, either by washing with ethanol or just leaving it vertically in a container so that it can float off. And after that, this polymer, hopefully with also enough polymer inside of the cells, is then polymerized. Sorry, this is of course not a polymer in this case. It is here a polymer in this point, after the polymerization by 70 centigrades over 24 hours. So this is the chemical fixation here in this case, using this resin embedding and staining protocol. So in the end, it looks like this. So in the ideal case, you see both your structure and your cells, so that you can easily then for later preparation find the site of interest where you can see where you want to investigate the interaction of your cell with your structure on top. Next thing. So if you're not interested in the inside so much of your sample, but mainly on some other structural points of your cell culture on top of this, you go through the critical point drying process in this case. The sample should be fixated and properly rinsed and dehydrated to 100% ethanol and should have a suitable size. So these samples here are in the sample holder already under the liquid, ethanol in this case. So, and then again, without falling dry, you transfer them into this recipient of the critical point drying machine, taking care that they do not fall dry under any circumstances. And then you close the lid and then slowly and stepwise you exchange the ethanol stepwise by liquid carbon dioxide. Once this process is done, and all of this is now only liquid carbon dioxide in this case, you can see simply by raising, you just start the machine in this case. In the beginning, this is cooled. Then you switch over to heating. And then if heating reaches or crosses the critical point in the phase diagram is the very point where liquid and gas phase meet and they lose their individual properties. So this supercritical fluid is neither a liquid nor a gas. It has no surface tension anymore. So in this case, you avoid these enormous forces, mechanical forces that would act on your structures if you would leave it drying on air. This critical point here is around is at 31 centigrades and a pressure of 74 bar. So you go a bit further than that. You go into the supercritical region. You do not want to reach only the critical point, but to go over this point. And after you reach this this region in the phase diagram, you carefully release the supercritical fluid until all of this is gone. The needle is here at 0 again, and then you can open the lid and remove your dry sample for further investigations. Next thing is, if you want to avoid these kind of chemicals for fixation in the first place, because you fear that you may change and alter the properties of your sample, then another method would be to use cryo fixation in this case. In this case, I have a TEM grid with possibly cells on top, and then this this sample is then moved rapidly into a liquid propane container with temperatures around minus 180 centigrades. So this is cooled here with liquid nitrogen, and what is also very important, that you have a cold nitrogen vapor atmosphere on top of this one. This makes handling of these samples later a little easier. You use propane in order to minimize the Leidenfrost effect you may have heard of. This is the one effect that lets drops of water dance around on hot plates without immediate evaporization. A protective layer will be formed that stops the temperature from decreasing any further. Quick enough, because you want to quickly, very fast, cool your sample down, because you want to avoid crystallization. You want to vitrify your sample. That means you want to have amorphous ice, not ice crystals, because as we all know, the density of ice is far lower than, for example, in the liquid. And this is what we try to avoid. Otherwise, we would experience ruptures and things like this and other destructions here. So this is one of these commercially available, not anymore, machines, but there are many others available on the market in principle. So here in this part, you condense the propane, for example, or methane, or a mixture of both, because at these temperatures, at liquid nitrogen temperatures in the other part around here, it would be a solid. So you can mildly heat this a bit so that it's kept a liquid. And then here with this piston, you can very rapidly push your sample into very fast into this propane in here. After that, with the help of a complex transfer, of a complex transfer machinery, you you put your sample, in this case here, for example, 10 grid holders here, pre-tilted ones, or a silicon wafer into this transfer shuttle. So with the help of this docking station over there, and then attach it to this other machine that is capable, for example, sputtering the frozen samples, which is necessary. And other things are also possible in there, for example, cryo etching, or for example, freeze fracturing. Freeze fracturing means with a cold knife, with a cold blade, you break open some of your samples. Here we did this accidentally with a sample, with a cell, a frozen cell on a surface. So you see the membrane, something from the inside, and something that could possibly be identified as the nucleus of the cell. But it is not a microtome. You cannot make very thin cuts with this one for TEM, for cryo TEM, for example. There are other machines available. There exist commercially available cryo microtomes, for example, but we don't have them here. After all this is done, so you have your sample in there, frozen, sputtered, maybe even etched, first etched away a bit of excess, water. Then you can transfer it again to a microscope or a focused ion beam machine, again, while maintaining the cryogenic conditions. So brings us to the next point. So is metallizing the surface. So metallizing in this case, as I said before, the samples for SEM should be electrically conductive, which they are not when they are frozen, for example, or resin embedded. So metallization means you add a few nanometers of metal on the surface top in order to dissipate both charge and also heat. Remember that your materials, your polymers, cells, and things like this tend to be damaged in an electron beam simply because of the heat in there. And so this may also stop this also a bit, or minimize this effect a bit. Very popular is gold in most cases, but we don't use this here because the grain size of this of the individual metallic layer plays some role if you want to observe a finer structure. Gold has, for example, a grain size from 8 to 12 nanometers. Platinum is what we prefer for biological samples. It has a grain size of 2 to 3 nanometers. Or for other samples where it's very important for nanostructured materials coming from the clean room, for example, we prefer iridium. This has a very small grain, smaller than 2 nanometers. We also use carbon for covering the surfaces, or for not protecting, not exactly metallizing, but to make the surface conductive with carbon, but mainly for EDX, where we do not want to add extra lines to our spectra. Again, here, this can also be done for platinum or gold under cryogenic conditions. So, and then we're done. So now we would like to see what is inside. So we have our sample, in this case, fixated chemically, stained with some chemicals, heavy metals, for example, resin embedded, polymerized. Yeah, and now we identified a certain range, or a certain site of interest. And then the first thing that we do here is with this electron beam deposition procedure, we add first a protective layer of platinum or platinum carbon. I've referred to this as platinum in the future, even though I'm very well aware that it's not just that. Roughly around 200 nanometers in order to protect this from the next following step that will involve the ion beam. And the ion beam will clearly destroy the surface, we will later see. So that's why we protect this first with this electron beam. And this is a very inefficient procedure. This takes some, what do we have here? Some roughly 20 by 20 by 15, 20 by 15, sorry, micrometers, and this took some 45 minutes, this step alone. The next step after that, we add a ion beam deposited layer, a bit thicker. We need this really as protective layers in order to minimize or to avoid artifacts by using the ion beam and by ion beam milling, for example, the infamous curtaining effect, for example. So here we apply some 1 micron. This is far faster than the first step. Now we have these protective layers here on top. So here you see what happens if we're done with the ion beam, because we also need to adjust the ion beam first and focus and do all these stuff, and you see the surrounding parts are degraded greatly here. So next thing, we do some rough milling. Yellow also always means taking away something. So the electron beam removes material from here quite quickly, quite rough. So we would like to have a look at the center of our cell here, for example, what we suspect to be a cell. And at the end of this process, it looks like this. We have a huge trench in here, looks very dirty here. So in the end, we end up here. After that, we start a couple of cleaning processes here with a very small current in this case, in order to clean the surface several times until we first get a nice surface, and second reach the point of interest where we can see both the cell and the structures here inside. After that, because we introduced here heavy metals, we image both with backscattered electrons here in this case, because we would like to make use of the Z contrast. For the cryogenic samples, for the cryofixated samples, it looks a bit different. First, we have here again our fixated sample on a cooled stage inside of the focused ion beam machine, for example. We identify again a cell on a structure that we would like to cut. And then next, what we will do here is we cannot, unfortunately, under these conditions, use the EBIT or IBIT procedure, because under these conditions, neither the ion beam nor the electron beam is able to decompose the precursor properly. So we just deposit the precursor on top of this one, so it looks a bit messy around here. After that, we cure the surface by simply prolonged irradiation or irradiating of the area of interest. Here you can clearly see some charging effects already, because the precursor molecule is a wax-like insulating material. After some time, you see it here from this field, it looks slightly better. The conductivity has improved, and we have our protective layer here on top. After that, same again, defining a field where we do some rough milling, first removing roughly some part of our sample here. After that, a few cleaning steps, and then after that, imaging. That means, and in this case here, well, we observe here with secondary electrons, also seeing still some charging effects. And after that, using backscattered electrons, they are less prone to charging effects. So that's why we have a better better image of what is inside and how these cells somehow interact with the structures in here. What we see here is something that we refer to as curtaining effect. This effect would be far worse if we would not apply a layer like this on top. Then in some cases, we will not see anything at all. Because you must, cutting with an ion beam is not like cutting with a clean knife, but it's more like sand milling or something. So what stands up on the structure will stand up even at the processed surface, even though the original particle, for example, is gone, but it has protected the underlying layers, for example, leaving behind these grooves here, these scratches. For cryo-TEM, the things are a bit different. These investigators let their cells grow directly on filmed TEM grids. And then somehow with, for example, fluorescent microscopy, they identify their cells or their sites of interest. And then with a very shallow angle, they produce, again, in a focused ion beam machine, a freestanding a freestanding TEM lamella or a lamella, which looks like this in the end from top view, not exactly top, and from the side it looks like this. And this goes directly into a cryo-TEM where they, for example, record tilt series of your respective molecules somewhere here inside that you may guess here. And then again, with lots of math, and they can reconstruct these molecules, ribosomes, for example, afterwards on the basis of such images. Yeah, the regular room temperature TEM lamella preparation goes as follows. Again, identifying the site of interest, first applying both E-beam and E-bit and I-bit platinum on top. After that, milling free at the front and at the back, so that we have a slab here standing free here, or chunk standing free, only connected with a small bridge here over time. Cut this free with this L or J cut in sometimes, so that it's only connected with a small bridge here to the sample originally. Then a lift out needle, again with I-bit, is welded or glued to the sample. Then the last remaining connection is cut away, and this the chunk is directly connected to this lift out needle, then dragged out or put out of the taken out of the trenches that we just prepared, and then attached to a lift out grid, and then glued back to this lift out grid here again with this gallium beam induced vapor deposition. And then after that, the needle is cut off, and then this chunk here is over different steps milled down to electron transparency until we do not see anymore. Is it 3 kilovolts? Until we do not, it's so thin that the sample does not produce enough secondary electrons, and this then again goes to where TEM. Here's a light microscopic image. Here is the TEM grid in this case, and this goes to a TEM. And in this case, if you have a crystalline material, then you can see atoms here in this case, or columns of atoms. These dots do not represent individual atoms, but they represent columns of atoms in this case, but here you can see the crystal structure clearly tell uh, how this is received. I cannot tell you more about this sample because it's not mine. So, okay, I would like to thank the group I'm working with here, of course, with to Stephanie, who made a lot of these images and helped me a great deal here with all of this. Anja, Kevin, um, Sascha, Marike, Kaylee und Daniel. And from IBI3, of course, I would like to thank Elke, Brauweiler-Reuters, Colin Fernandez, and Yannick Rutsch. Thank you very much. It's a bit fast and early. Sorry.
Thank you very much for a very enlightening talk. I think we are going to stop the recording here, and then we